Welcome to this advanced hire video looking at the electromagnetism unit and in particular applications of electrical charges in electric and magnetic fields. So these are the three learning outcomes that we're going to look at. So looking at relationships to solve problems for charged particles in magnetic fields, a brief reminder of helical motion of charged particles in magnetic fields, and solving relationships of the motion of charged particles in electric fields. So in particular, we're going to focus on applications where we have magnetic and electric fields, but we will revisit some of the underlying theory from previously in the topic briefly. So let's remind ourselves what a field is. So it's a region of space around a particle where we experience a force. And we can have three different types of fields: electric fields, where electrical charges experience a force; magnetic field, where a moving electrical charge experiences a force; and a gravitational field, where something with mass experiences a force. One of the big differences between gravitational forces and the other two is that gravitational forces are only ever attractive, whereas the others can be attractive or repulsive. So one of the pieces of equipment we can use in the classroom is a cathode ray tube, and we can use this to study electric fields and magnetic fields. So the electrons are produced at the negative cathode, so that's here, and there is an electric field at the positive anode, which is pretty much here. You can see the lead is connected to that point there. Okay, this one that's coming up here. And the electrons here are accelerated in that direction towards the anode that has the opposite charge, and the kinetic energy that's gained by the electrons is equal to the work done on the electron by the electric field. That work done is Q, the charge, times the potential difference between the cathode and the anode, and since that is equal to the kinetic energy gained, half mv squared, where in this case m is the mass of the electron, we can work out the speed that the equipment would be producing the electrons at. These electrons can be deflected vertically by the plates at the top here. So if we just highlight at the top or the bottom of the part that's the screen, then in this case the electron is being deflected upwards. So if this was due to the electric field, actually in this case it's due to the magnetic field, but if it was due to the electric field, then we could connect this wire here to positive, and the wire at the bottom there would be connected to the negative terminal, and we could deflect between these two plates. So between these plates at the top and the bottom, we've got a uniform electric field, and we can work out the electric field strength from the potential difference between these two and the separation between the two plates, the distance d that would be across there, and that would allow you to work out the force on that electron. And it's following this curved path, presuming the magnetic field is off, as a result of constant horizontal velocity and a constant vertical acceleration due to this electric field. We can work out the deflection from the middle point of that there. So if we rub that out and say, well, what would be the deflection from there to there? S. We could do that using an equation of motion. So we need to work out what the acceleration is due to the electric field, and then use the equation of motion and the time to work out what the displacement is. The time can be calculated from the horizontal length that the electron is in the field for, which would be this distance in that direction, and the speed that the electron's coming out horizontally from the gun over there. Okay, and this is the work that you've been doing earlier in the unit from there. Okay, so we can also use the same equipment with the electromagnets called Helmholtz coils to provide a constant magnetic field. So these are these green circles, the black circles that are indicated in there. Underneath those, there's one either side of the tube, and underneath those are lots of coils of wire. And down here, we've got connections to those, and those go to a power supply, a variable power supply, where we change the current flowing through these two coils of wire. There's one either side of the tube itself. The tube itself is sort of circular, spherical in shape, and there's one fits one side and one fits the other side, and between those two there's a uniform magnetic field. Is how they're connected to get that situation. And when the electrons enter perpendicular to that field, they experience a force at right angles to their motion, and so they can follow this curved path because of the force due to the magnetic field that's acting upon them. So, little reminder about magnetic fields. Since we've got the motion being perpendicular to the magnetic field, and we've got three possible dimensions, then we can show this as crosses going into the page, like that, would show a field going into the page, or dots coming out of the page to show the field coming out of the page. We'll recall from our higher physics that we can use our right-hand rule to determine the direction of negative charges, where our thumb is the force, the direction of the force on the charge. Our first finger is the magnetic field, and our second finger is the direction of the negative charges. You can use the left-hand rule if you want to look at it for positive charges, or you can continue to use your right-hand rule for positive charges, but you have to point your second finger in the opposite direction for a positive charge motion. So let's have a little look at this one here. So if we point our first finger into the screen, because we've got crosses for the magnetic field, our thumb currently is pointing up and our second finger is pointing to the left, and we can see that the electron is actually going from left to right, so we need to turn our hand upside down, keeping our first finger pointed in. Our second finger should now be pointing to the right, and our thumb is pointing downwards with the direction of the force. Okay, as it moves around and changes direction, then there's still a direction to the force towards the same direction. So when it comes at this point here on the side there, the force arrow is that way, and that's because the velocity arrow is now in this direction. And so we end up with circular motion because we've got force acting towards the center of the circle in the continuing changing direction. Here's another example you could stop the video and have a look at, just to check that you're able to indicate the correct direction for the force. And you can either use your left hand here, or you can use your right hand and point your finger in the opposite direction to the velocity arrow. Okay, so both these diagrams are correctly showing the direction of the forces. Make sure you're able to use your right hand to work out the directions. Quick reminder of what we mean by magnetic induction, or the magnitude of the magnetic field. It's got the symbol B, measured in Tesla, and it's defined as the magnetic induction needed to produce a force of 1 Newton on a conductor of 1 meter carrying a current of 1 amp. And this is coming from F equals B times I times L. So we've got 1 Newton is what force we get if we have 1 Tesla and 1 amp and 1 meter. Okay, so how might we measure magnetic field strengths? Well, one of the things we can use is we can use the Hall effect and a Hall effect probe. So if we place a conductor perpendicular to a magnetic field and we pass a current through this material, so we've got the current I going from right to left on this diagram here, we've got a field going into the page on the diagram there. So if you hold out your right hand, you can see that there will be a force on these electrons that are flowing from right to left upwards. That's the way your thumb is pointing. So what happens, as shown in the second diagram, is that these electrons follow this curved path to the top. So the top of the block becomes more negatively charged than the bottom of the block because there's been a drift of electrons towards the top there. And what we can then do is we can attach a voltmeter to the top and the bottom surfaces, and we end up with a potential difference, a voltage between these two. And this is what is used in a Hall probe to measure the strength of magnetic field. So you can place this conducting material within your magnetic field and you can measure what voltage is produced. Now, if you place it within particular things, so a solenoid, a coil of wire, you get a uniform field relating to the current, so you can calibrate the voltage that you measure in millivolts to the field strength that you're expected to get, and then you can measure it in an unknown situation. Okay, so a reminder from the quanta unit that we discussed the force acting on charged particles, and the force due to the magnetic field depended on the magnetic induction, the charge, and the velocity or speed of the particle that was moving. Okay, so we've got B times Q times V. And when it's acting at 90 degrees to the motion, we get that circular motion which we saw on the previous diagram. So we can use our knowledge of centripetal forces to determine the radius of the path. So if we got a charge entering, like the picture on the right here, entering our magnetic field going into the page, we've seen that there is a force downwards, and we end up with a circular motion because when it's at the right point on there, we've got a force arrow that's going that way. When it's down here, we've got a force arrow that's going that way. So we have circular motion at that point. So by considering the forces, why does it move in a circle? Well, it moves in a circle because of the force due to the magnetic field. That is our centripetal force. B times Q times V is mv squared over r. We can cancel one of the v's, we can rearrange to work out the radius. So the radius is going to depend on the mass and the velocity of the charge, divided by the magnetic field strength and the charge of it itself. So we can look at what the effects are going to be if the charged particle changes, if it's going faster or slower, or has a greater or lesser charge. And that's what the next example is going to have a look at. Okay, and there's lots and lots of applications about studies of charged particles in this way. So we've got an electron accelerated by an electron gun into a 0.5 millitesla uniform magnetic field, and it has a particular velocity. And we're asked to calculate the radius of the circular path in the field. So the relationship for the radius isn't one that's given to you, so you have to derive it. The question may ask you to show that the radius is this because the charge in the magnetic field follows a circular path. So B times Q times V is mv squared over r, rearrange, and then substitute in the mass of the electron, 9.11 times 10 to the minus 31, and the charge on the electron, and the other information. Okay, that information on electrons is on the data sheet in the front of the exam paper. Okay, so let's look at a bit more information. What happens if we changed it to something else? So we've got some different values of other nuclear materials. So we've got a neutron which would have no effect in a magnetic field because it's got no charge, but we've got an alpha particle and a proton that we could be looking at. So we might be asked a question, what would happen to the radius if we increase the velocity? And this could be a state where you'd say, well, V is going to go up, so R is going to go up. So increase would be enough, or it could be a state and explain or justify where you'd have to describe that it increases, but it increases because the velocity increases. So we replace our electron with a proton. It's moving at the same speed. What happens now? Well, the proton has a greater mass than the electron. If we look at the masses there, much greater, nearly 2,000 times greater. So if the mass is greater, the radius is going to be much greater. The charge on both is the same. What is different is that one has a positive charge and one has a negative charge, so one will curve one way and the other one will curve the other way because the force will be in the opposite direction. That's seen by the picture underneath the data table there, where we've got a picture this time of an electron and a positron. Positron is an anti-electron, so it has the opposite charge, same charge as the proton, but the same mass as an electron does. And so it's spiraling in the other direction because it has the opposite charge. It's going in circular motion, but not in the same direction. Okay, so we replace the electron with an alpha particle, moving at the same speed. What happens then? So consider the changes that we've got. So the mass has changed, and we can see there that the mass of an alpha particle much bigger than the mass of an electron. The charge has also changed. The charge on the alpha particle, it's got 2 protons, so it's got +2 instead of -1. So that's going to reduce the radius. But the mass has gone up so much more than the charge has gone up that there's going to be an increase. And we could work out how much. If we look at how much the mass is different, it's about 7,000 times those numbers in the table. And even though the charge is double, we're going to end up with 3,500 times approximately greater radius than we had beforehand. Okay, so you might be asked to state what the change is, or most commonly you're asked to explain and justify your answer. So you refer to the equation, talk about what stays the same, what is changing in your explanation. You could do a full calculation, or you can just talk about the trends of the increases. Okay, so a little reminder about helical motion. So the example we've just looked at, the charged particle was going entering the magnetic field at an angle of 90 degrees. If it isn't quite like that, then there will be a component of the velocity. There will be one that is perpendicular at right angles to the field, which will cause the circular motion, and there'll be one that is parallel to the field that will just cause it to move to a different place, what we call linear translation. And what we end up with is helical or spiral motion, like the picture at the bottom. So the electron is moving in a circle if we looked at it from the end point of view, but it's moved in space because of the constant horizontal motion. So the pitch, the distance between it, the length of the line here, the blue line here, that would be equal to the horizontal component, your parallel component to the field. Sometimes you use V with 2 bars to show it that it's like parallel, times the time that it took to do one rotation of the motion. Whereas the component that you'd be interested in terms of your BQV from your radius that we've got would be your perpendicular component, which is sometimes written as V with a kind of like a right angle part there. So you'd have to solve one way to find the time, and then the other way. If you're trying to find the time, then it would be the period of the rotation that you'd need to look at. So what is the distance for that circumference divided by the speed that we've got the perpendicular component. Okay, so let's have a look in Kate's situation of both of these coming into play, where we've got a magnetic field and an electric field, and they're arranged 90 degrees to each other so that the field will move one way and the other field will be in the opposite direction. So if we've got a particular charge here, let's say it's an electron, so the charge due to the electric field on the electron that I'm going to draw in green, let's say here's our red particle, so that's going to be attracted upwards like so. That'll be the force due to the electric field, Fe. And if we use our first finger into the field, second finger direction of negative charge to the right, our thumb is pointing down, so we've got the force due to the magnetic field acting downwards. So we've got Fe acting upwards, force due to the electric field upwards, and the force due to the magnetic fields downwards. And this arrangement equipment is called a velocity selector for reasons that will become apparent. So we've got the magnetic field upwards, Q times V times B. We know that from our right hand rule, so you would have to check the direction to see if that works out okay. So in this case, it's going upwards. And we've got the electric field going downwards. So because we're talking about a positive ion in this particular example. Okay, so in this case, it's upwards and the other one's downwards. So it depends, but they're in opposite directions. And the electric force downwards is Q times E. And when the forces are balanced, those two are equal. You can see that we can cancel out the charge there because it's in both terms, and then we get that the velocity is equal to the electric field strength divided by the magnetic field strength. So ions of this particular velocity will have an equal force upwards and downwards and will move through both fields undeflected. So it doesn't depend on their mass at all. And it doesn't depend on the charge. It just depends on their velocity. So what might this look at? So we've got protons being fired from a particular source into a magnetic field. Now, of course, for them to be fired, then there would need to be an electric field to accelerate them. But we're just focusing on the section that has the electric field and the magnetic field perpendicular to each other. We're given a value for the magnetic field strength and the potential difference and the plate separation for the electric field. Calculate the electric field strength. Well, the electric field strength is V divided by D, the potential difference 2.5 kilovolts divided by the separation in meters. The force due to the electric field is Q times E. Here the charge on our proton times our earlier answer. Okay, determine the speed. If it passes through undeflected, then the force due to the electric field and the force due to the magnetic field are the same. And so the speed that we need for that will be the electric field strength divided by the magnetic field information, which is in the question above. So that gives us 2.17 times 10 to the 5 meters per second for the speed that will be undeflected. If we fire an alpha particle, which has twice the charge and 4 times the mass, what effect does this have on the velocity that it needs to have to pass undeflected? Well, and we have to justify our answers. Well, the velocity depended on the electric field strength and the magnetic field strength. Neither of those have changed, so it will have no effect upon that at all. And the velocity that we will need will be the same as the one that we worked out earlier 2.15 times 10 to the 5, 2.17 times 10 to the 5 meters per second, because it doesn't make a difference that the mass has changed or the charge has changed. So a mass spectrometer works in this way. There is the ion source, there is this cross field in the first section that we've got there, so this part here, and then in the section over here we have our magnetic field. So this is a electric field and a magnetic field, and the second one is the area where there is just the magnetic field taking place. And we've already seen that it doesn't matter what the mass is or what the charge is, the same velocity of ion will come out at the end here, will be undeflected. So things that are moving slower or faster will be deflected and will not get through that gap in the plates there, but things that aren't won't. So we selected that particular velocity. They then enter the magnetic field, and just as we were talking about earlier, they experience a force due to the magnetic field. This time the field's coming out the page. So if you point your finger out the page and you've got your direction of the charges, these are positive charges in this case, then you can see that you're going to get a force. Your thumb is going to point downwards, which is of course the force that we would need for it to be able to move in circular motion, and the force would be going in those kind of directions from there. Now if they have different masses, then they will follow a different circle, because on the right hand side the radius of that path depends upon the force that acts upon them. And the force that's acting is the magnetic field strength, which is the centripetal force, because they're moving in a circle, and we've got our radius. And our radius depended on the mass. So the greater the mass, the greater the radius that we've got there. So different samples, mass 1 hits at this point, mass 2 with a greater mass hits at a greater radius. Okay, notice here we've got the 2 times the radius, because that's the diameter of the circle rather than the radius that's being shown there. And this is used for our mass spectrometer. They don't get things moving entirely in a semicircle, but they do work in the same way. So we've got the sample entering at the beginning. It is vaporized. We ionize it by adding electrons. It's then accelerated across the electric field, the 2 plates that are shown there. It then travels into the magnetic field, and then it is deflected and detected at the end. Okay, finally, just to mention about the charge to mass ratio of an electron. So J.J. Thomson in the Cavendish laboratories in Cambridge was the first person to measure the charge to mass ratio of an electron. He wasn't able to measure the charge or the mass of the electron, just the ratio of the 2. It was Millikan's experiment that measured the charge. And he did this because he got the electron deflected by the magnetic field. So we've got our deflection tube with the electron being deflected by the magnetic field in a circular path. That path there is part of a circle. You can work out what radius of the circle would be from that by taking coordinates from it. And by saying that the centripetal force is equal to the magnetic force, you can rearrange that relationship to give the charge divided by the mass, Q over m, or often E over m, with E being the charge on an electron. And you find it depends upon the speed of the electron, the magnetic field strength, and the radius. So he was able to measure the radius by taking coordinates of the line. He could measure the magnetic induction, what the magnetic field from the Helmholtz coils, the black part on the picture was, and he could measure the speed of the electrons as they entered from the work done by the electric field that he knew the potential difference of. And this allowed him to solve the charge to mass ratio, and in combination with Millikan's experiment we were then able to work out the actual mass and of the electron from there. Okay, so the things that we've dealt with in this video are to solve problems for magnetic fields and electric fields.